Deep in the cosmos past, before humanity existed, light began a journey unlike any other. Not just the physical movement of photons across space, but the deeper story of a universe slowly becoming aware of itself. That ancient light carried information from epochs so remote that time itself feels distorted when we try to comprehend it. And only now, after billions of years, beings made from the same cosmic material finally built machines capable of receiving those messages. But the James Webb Space Telescope did more than observe ancient light. It uncovered evidence that challenges the story we have spent the last century constructing about the universe's origins and evolution. These are not minor inconsistencies that can be patched with small adjustments. They are discoveries that suggest our entire framework for understanding cosmic history may be incomplete. Perhaps Einstein's equations never described the full picture, or perhaps reality has always been far stranger and larger than we imagined, and only now do we possess instruments powerful enough to force us to confront it. This is not simply a story about science being wrong. Science thrives on correction. It advances by questioning itself. But what Webb revealed feels deeper than that. It suggests that the questions we asked about the universe may have been too narrow from the beginning, that the map we created of reality described only a small region of a much larger landscape we had not yet imagined. And that realization changes not only what we know, but the very way we think about knowledge itself. Imagine walking through a museum where every artifact contradicts the history you expected to find. In one room, where you anticipated primitive pottery, you instead discover intricate sculptures. In another, where crude tools should exist, you find sophisticated machines. Each exhibit dismantles the timeline you arrived with. At first, you assume the labels are wrong. Then, you verify the dating methods. The dates are accurate. The objects truly are as ancient as claimed and as advanced as they appear. Eventually, a more unsettling possibility emerges. Perhaps civilization developed far faster than anyone believed. Perhaps complexity appeared much earlier. Perhaps our understanding of development itself was incomplete. That is the situation cosmology now faces while examining Webb's deep field observations, a museum filled with impossible things. Astronomers expected the earliest galaxies to be small, chaotic, and unfinished. According to established models, galaxies needed immense stretches of time to grow through mergers, star formation, and gravitational evolution. Heavy elements had to be forged inside stars, scattered through supernova explosions, and recycled into future generations of stars and planets. The sequence was logical. Gravity is slow. Structure takes time. The physics appeared solid, and the predictions seemed reliable. Then, Webb looked into the infant universe and found mature galaxies already in place. Not rough beginnings or tiny proto-galaxies, but enormous systems containing hundreds of billions of stars. Some already displayed organized disk structures and evidence of multiple generations of stellar evolution. These galaxies appeared less than 1 billion years after the Big Bang, astonishingly early in cosmic history. It was as if someone opened a photo album of a newborn child and discovered a middle-aged adult staring back instead. Naturally, astronomers first suspected error. Perhaps the distance measurements were inaccurate. Maybe dust or brightness effects distorted the observations. The early universe had fooled scientists before. But then, spectroscopy, astronomy's most reliable verification tool, confirmed the findings. By splitting light into precise wavelengths, researchers could measure redshifts and chemical signatures directly. The galaxies truly were as distant, massive, and mature as they seemed. And the deeper scientists looked, the more troubling the pattern became. It was not just a handful of anomalies. Dozens of galaxies appeared too massive, too chemically evolved, and too organized for such an early era. Then the number grew into the hundreds, observed across multiple surveys and by independent research teams. The evidence became impossible to dismiss. The problem was no longer the observations. The problem was the story itself, each generation of stellar death seeding the next generation with heavier elements. All of this takes time, tremendous amounts of time. The first stars in a galaxy must be born from primordial hydrogen and helium. These early stars are massive and short-lived. They burn through their fuel rapidly. When they explode, they spread heavier elements through the surrounding gas. Only after those explosions can a second generation of stars form that can incorporate those heavier materials. That second generation can be slightly longer-lived. They can spread more variety of heavy elements. Eventually, after multiple cycles, a galaxy reaches what astronomers call chemical maturity. It contains a rich diversity of heavy elements forged across generations. It shows the scars and rewards of evolutionary time. The galaxies Webb found in the early universe showed precisely these scars. They looked chemically mature. They looked like systems that had undergone multiple generations of stellar birth and death. They looked like they had been evolving for billions of years. But the universe itself was not billions of years old. It was less than one. The contradiction was absolute, and no simple adjustment could resolve it. Some researchers proposed that star formation in the early universe was simply far more efficient than in modern galaxies. Perhaps nearly all the available gas collapsed directly into stars instead of the usual small fraction we observe today. That would explain the brightness. That would explain the stellar mass. But it creates a secondary problem. Radiation from stars pushes back against collapsing gas. If too many stars form too quickly, the radiation becomes powerful enough to halt further collapse. The physics resists it. The universe has limits built into its operating system, and those limits were being violated. Others suggested the stars themselves were simply bigger and hotter than modern stars. If the early universe naturally produced supergiant stars with enormous luminosity, then less total stellar mass would be needed to explain the observed brightness. That would soften the problem. But it could not eliminate it. The spectroscopic signatures did not match simple brightness overestimation. The galaxies truly were massive. The chemical enrichment truly was present. The maturity truly was real. The deeper astronomers looked, the narrower the escape routes became. Layer by layer, alternative explanation by alternative explanation, the data eliminated options, until finally, a harder truth emerged. Either the rules governing galaxy formation were incomplete, or the cosmic timeline was wrong, or something was providing a shortcut in the assembly process that nobody had predicted, something that accelerated structure in defiance of standard expectations. The hidden architects. That is when attention turned to the monsters hidden inside the galaxies Webb was observing. Black holes. In the standard model, black holes are side effects. A massive star exhausts its fuel. Gravity wins. The star collapses. If the mass is high enough, a black hole is born. It is an end point, a consequence, a thing that happens when stellar evolution reaches its conclusion. Black holes are not supposed to be architects of structure. They are supposed to be accidents. Yet Webb was finding evidence of supermassive black holes in the centers of these impossible early galaxies. Black holes weighing millions or even billions of times the mass of the Sun. Monsters that should have taken hundreds of millions of years to grow from stellar seeds. Yet they appeared only a few 100 million years after the Big Bang. The black hole growth problem became as acute as the galaxy maturity problem. And then, remarkably, attention turned to something that might connect them both. What if the first black holes were not accidents? What if the early universe did not begin with stars and planets and gradual structure building? What if it began with gravitational collapse on a much more fundamental level? What if, in the first fractions of a second after the Big Bang, before atoms existed, before light could travel freely, before conventional physics had fully settled, some regions became dense enough to collapse directly into black holes? These would be primordial black holes, fossils from the universe's first heartbeat, ancient gravitational seeds hidden inside the cosmos from its very beginning. Unlike stellar black holes that start small and grow through feeding, Primordial black holes could be born massive. Hundreds of thousands of solar masses. Perfect seeds for early galaxy formation. Drop such a seed into a cloud of gas and gravity does the rest. Structure organizes around the dark center. Stars gather. A galaxy forms. Billions of years of stellar evolution becomes unnecessary. The shortcut appears. Suddenly, multiple mysteries connected. The impossible galaxies had their seeds provided. The black holes had their head start granted. Structure could assemble quickly because the invisible scaffolding was already in place from the universe's first moment. But this raised an even more disturbing question. If the universe began seeding itself with black holes from the start, what was the universe actually made of in its first moments? And what could create such extreme density so early? The answer pointed back to something even deeper. A bouncing universe. A contracting universe that compressed matter beyond all recognition, beyond all normal physics, into density so extreme that quantum effects took over, that gravity itself became unstable, that space-time curvature reached limits no human equation had properly described, and then something happened that should not have been possible. The contraction reversed. It bounced, like a cosmic spring compressed to maximum tension and released. The result was the expansion we call the Big Bang, the fingerprints of birth. But if the Big Bang was not a true beginning, if it was a bounce from a prior phase, then something else followed inevitably. The new universe would inherit properties from the prior one, not consciously, not through design, but through conservation laws. Angular momentum cannot be created from nothing. If the prior universe was rotating, even slowly, that rotation would be preserved. It would be compressed during the contraction phase. Then, as the new universe expanded, it would be stretched across cosmic scales. Subtle, almost invisible, but structural. That inheritance would leave marks. Marks that would show up in how matter distributed itself across space. Marks that would appear in the rotation patterns of the galaxies that eventually formed. Marks that would create a slight directional preference, a bias, a memory of the mother universe's motion encoded into the children. Webb found such marks. Or rather, Webb found hints of such marks. When researchers analyzed the rotation directions of spiral galaxies in the deep field images, the numbers refused to balance. Too many spiraled one direction. The asymmetry was statistically small, but statistically real, like flipping a coin hundreds of times and getting heads far more often than random chance predicts. Once is luck. Twice is coincidence. Repeatedly is evidence that something deeper is operating. In a random universe, this should be impossible. Isotropy is one of the deepest assumptions in cosmology. It means that on sufficiently large scales, the universe should look the same in every direction. No preferred orientation. No cosmic handedness. No built-in bias. But what if that assumption was only approximately true? What if beneath the apparent uniformity, a subtle twist existed? A faint, angular momentum. A small but ancient rotational preference carved into the fabric of space-time itself? If so, that preference could only mean one thing. The universe was born rotating. And if it was born rotating, something had to give it that rotation. Some prior condition. Some earlier state. Some parent structure existing before what we call the beginning. That pushed the question backward, beyond the Big Bang itself, beyond the event we had always treated as absolute origin, beyond the beginning. That is when black hole cosmology stopped being philosophy and started being cosmology, the nested infinite. The idea sounds like science fiction the first time you hear it. Our universe exists inside a black hole, not as a metaphor, not as poetry, as geometry, as physics, as mathematics that works, and works consistently. Think about what a black hole actually is. Not the pop culture image of a cosmic vacuum cleaner. The physical reality. A black hole is a region of space-time where curvature becomes so extreme that all possible paths lead inward. It is not that objects choose to fall in. They have no choice. Moving toward the singularity becomes as inevitable as time moving forward. The center becomes a place of infinite density where normal physics ceases to describe reality accurately. Or does it? What if the infinity is not real? What if it is a symptom of theory reaching its limits? In that case, something else might happen at extreme densities. Perhaps quantum effects take over. Perhaps space-time itself has properties we have not yet discovered. Perhaps the collapse does not end at a singularity. Perhaps it bounces. Space compresses to maximum density, then reverses course. A new region of expanding space-time emerges. From inside that region, the phenomenon looks exactly like a Big Bang. From outside, it looks like a black hole interior that never reaches singularity. The boundary between the parent universe and child universe is the event horizon. Information cannot cross it. To the outside, the child universe is forever hidden. To the inside, the child universe is all that exists. If this is true, then our universe may be the interior of a black hole formed in a parent cosmos. The Big Bang was not creation from nothing. It was creation through gravitational collapse. Our expansion is not free expansion into void. It is expansion within a geometric bubble. Our time has direction, not because of some fundamental asymmetry, but because matter falling through an event horizon can only move one way. The arrow of time is inherited. Our rotation preference is not random. It is inherited from the parent black hole's spin. Suddenly, Webb's anomalies fit into a coherent framework. Not all explanations work equally well, but alignment itself becomes meaningful. When separate mysteries point toward the same deeper structure, science takes note. When a framework can accommodate multiple strange observations without adding ad hoc complications, scientists listen. But the deepest consequence is almost impossible to absorb. If universes are born inside black holes, and if black holes form in those universes, then every black hole in our cosmos may be pregnant with a new universe. Every collapse may be a birth. Every gravitational monster may be a cosmic womb. The universe does not just expand, it reproduces, it multiplies. It branches through gravity itself into infinite variations. A family tree of nested realities. Universes inside black holes, inside universes inside black holes, recursive and endless. And if that is true, then every black hole Webb finds in the early universe is not just a monster. It is evidence of reproductive activity. The cosmos beginning to populate itself with new universes almost immediately after its own emergence. That is not random. That is not accidental. That is systematic reproduction. The evolutionary universe. If black holes are reproductive structures, then something else follows. A mechanism of selection emerges. Universes that create more black holes create more descendants. Those descendants inherit physical properties from their parents. Over countless generations, selection would favor laws that produce black holes efficiently. Laws that create stars quickly. Laws that collapse matter readily. Laws that organize structure aggressively. In other words, laws that look remarkably like ours. This is cosmic natural selection. Not conscious, not designed, but real, blind, mechanical, operating at the scale of universes. A multiverse evolving its laws through reproduction. Universes with inefficient structure formation would leave few descendants. Universes optimized for black hole creation would populate the multiverse. Eventually, the multiverse would fill with universes tuned for complexity. Because complexity enables black hole formation, we would naturally find ourselves in such a universe. Because only such universes could have descendants complex enough to build observers. Only such universes could generate minds curious enough to build telescopes. Only such universes could create the conditions for Webb to exist. and to wonder why it exists. But this raises the philosophical question that natural selection always raises. Is life and intelligence and consciousness and the existence of observers incidental to the reproductive process, or are they integral? Are minds byproducts of structure optimized for black holes, or are minds essential to the cosmic reproductive cycle itself? Could intelligence be the universe's way of ensuring its own continuation? Could consciousness be built into the cosmic design not as goal but as consequence? Webb does not answer these questions, but by showing us a universe extraordinarily efficient at producing black holes and structure, it makes them difficult to ignore. Because Webb reveals a cosmos that seems almost optimized for building the conditions that eventually lead to observers. Not destiny, not design. Evolutionary outcome. Selection pressure favoring physical laws capable of creating minds. The problem of early monsters but Webb also revealed something even stranger than rotating galaxies and structure-optimized laws. Deep inside the impossible galaxies, and hidden within the cosmic dust, were objects that became known as little red dots. Tiny, brilliant, glowing deep crimson and infrared, too numerous to be accidents, too strange to be ordinary, too luminous for their size, too common in the early universe and too absent in the later cosmos. They appeared heavily in the universe's first billion years. Then they faded. They were a phase, a temporary state. Something turned them on. Something turned them off. That pattern itself is informative, because transient populations often reveal hidden evolutionary stages, ecological niches that opened and closed, growth phases that accelerated and terminated. The little red dots may be cosmic adolescents captured in light billions of years late. The simplest explanation was dusty galaxies. Dust absorbs blue light and remits infrared, making objects appear redder than they truly are. But the little red dots were too bright. Their luminosity far exceeded what dust alone could explain. They glowed like powerhouses in infrared, while remaining strangely quiet in X-rays. That combination suggested hidden activity, intense energy emission wrapped in thick, obscuring material. One object fits that description perfectly: a black hole feeding aggressively inside a dense gas cocoon. As matter spirals inward toward the event horizon, it heats to millions of degrees. That heat releases enormous energy. But if the black hole is surrounded by thick dust and gas, the high-energy X-rays are absorbed. Only the infrared radiation escapes. From a distance, the object appears as a glowing red dot. Small, bright, hidden, exactly what Webb was seeing scattered through the early universe. If that interpretation is correct, then little red dots are baby pictures of cosmic monsters, snapshots of supermassive black holes in their rapid growth phase. The universe building its central engines while still in its infancy, feeding aggressively, growing explosively, establishing the conditions for the galaxies that would later host them. The little red dots vanish after a certain cosmic epoch because the gas surrounding them disperses. The cocoon clears. The black hole transitions to a different state, no longer a hidden glowing point but an active galactic nucleus. Still powerful, but visible in different wavelengths. You are not separate from the universe. You are an expression of it, a concentration of cosmic matter that has become aware. That awareness now wonders about its own origin. That consciousness has built telescopes to see backward in time. That mind has asked questions that the universe itself may not have fully asked before. You are the universe studying itself, the cosmos achieving self-awareness through you. And that means the answers you find are not external knowledge. They are self-knowledge. Discovery about your own nature, your own origin, your own place in the larger structure of reality. The mystery that remains the deepest mystery may be the simplest one. Why is there something rather than nothing? Webb cannot answer that. No telescope will ever fully answer it. Because the question points beyond science into something more fundamental. Not metaphysics, but the ground of existence itself. Why does reality exist at all? Black hole cosmology offers a possible answer. Reality exists because its own structure demands it, because recursion is possible, because infinite nested universes can exist without requiring an external creator, because complexity can bootstrap itself, because something is more stable than absolute nothing. But that answer only works if you accept that the very laws of physics, the rules that govern black holes and bouncing universes and everything else, are themselves necessary. That there is something inevitable about them, something that could not be otherwise. Maybe that is true. Maybe the laws of physics are not arbitrary. Maybe they are the only laws possible under the rules of logic and mathematics. Maybe a universe without quantum mechanics or relativity or gravity would be logically impossible. Maybe our cosmos is not one of infinite possibilities, but the only possibility that the universe could take given the nature of existence itself. If that is true, then Webb is not discovering truth about the universe. It is discovering truth about necessity, about what must be true in any possible reality, about the constraints that make existence possible. The universe being stranger than expected is not a flaw in that interpretation. It is confirmation. It means the rules are deeper than we thought. The structure is more fundamental. The necessity is more profound. The light still arriving. As you read these words, Webb is still observing. Photons are still being detected. Light that left ancient galaxies is still arriving at the telescope. The cosmic drama is still unfolding. In a few years, new images will arrive. New surveys will be completed. New puzzles will be revealed. Some of today's mysteries will be solved. Others will deepen. The fundamental questions will shift and evolve. But something will not change. The fact that the universe is stranger than we imagined. The fact that complexity emerges earlier than we predicted. The fact that structure organizes more efficiently than we calculated. The fact that what we thought was complete was only a beginning. Webb has shown us that the cosmos is not finished telling its story, that revelation changes everything. Because it means the universe still has surprises, that science still has frontiers, that mystery still exists, even after a century of extraordinary discovery. The map of reality is being redrawn. The old lines are becoming obsolete. New territories are being revealed. Territories we did not know existed. Territories that may contain answers to questions we have not yet learned to ask. Sleep under that knowledge tonight. Above you, gravity is still bending space-time. Galaxies are still moving through the expanding cosmos. Black holes are still feeding on matter and perhaps birthing new universes. The universe is still computing itself into existence. And somewhere, photons that began their journey billions of years ago are still arriving, still carrying their ancient messages, still whispering of a cosmos far stranger and more wonderful than human imagination had prepared us to believe, still asking us the same eternal question: what are we? Where did we come from? What is the nature of this reality that birthed us? And what comes next? Webb has opened the conversation. The universe is speaking. And for the first time, we are finally learning to listen. The realization that our universe might carry the genetic material of an older reality changes the texture of every observation we make. It transforms the James Webb Space Telescope from a mere camera into a chronological archaeologist, unearthing artifacts that shouldn't exist because they belong to a time before our time. When we look at those impossible, hypermature galaxies standing tall in the deep freeze of the cosmic dawn, we are no longer just looking at a failure of our current galaxy formation equations. We are looking at a chronological mismatch. If the standard model says the soil was planted last week, and yet we are staring at an ancient, thick, canopied forest, the most logical conclusion isn't that trees magically grow 1,000,000 times faster than physics allows. The more profound, unsettling conclusion is that the soil was already fertile, seeded with the decayed nutrients of a season that passed before we started counting days. This is the hidden architecture that the data is forcing us to confront. If the early cosmos was preceded with primordial black holes, born not from the depths of our universe's first stars, but forged directly out of the hyperdense, turbulent twisting of a parent universe collapsing into a singularity, then the entire timeline of structure formation is liberated from the slow, agonizing crawl of hierarchical growth. In the old model, gravity had to do all the heavy lifting from scratch. It had to find microscopic, random ripples in a nearly uniform sea of hydrogen, slowly coaxing atoms together over millions of years to build a star, then waiting for groups of those stars to find each other, merge, and eventually build a galactic core. It was a bottom-up construction project where every brick had to be baked on site. But if the little red dots in the giant early galaxies are telling us a top-down story, then the engines were already running before the lights came on. These primordial black holes would act like massive gravitational whirlpools already spinning in the primordial soup, instantly pulling vast reserves of gas into structured, rotating disks. They wouldn't wait for stars to form. They would force stars to form by compressing gas through sheer, violent gravitational tidal forces. This explains the terrifying efficiency of the early universe. It explains why James Webb sees systems glowing with the heavy elemental signatures of oxygen, carbon, and iron in an era that should have known only the pristine simplicity of hydrogen and helium. The universe didn't rush through its infancy. It skipped it entirely because it inherited a pre-existing structural blueprint. This idea of cosmic inheritance completely alters our understanding of the cosmic microwave background, the faint, faded afterglow of the Big Bang that blankets the sky in every direction. For decades, we looked at the tiny temperature fluctuations in that ancient light and saw them as the random quantum fluctuations of a newborn universe, stretched out by an epoch of rapid cosmic inflation. We assumed those patterns were the result of pure quantum noise, a cosmic roll of the dice. But if the universe has a preferred direction, if the rotation of those ancient spiral galaxies points toward a global, structural asymmetry, then those fluctuations aren't random noise at all. They are a scar. They are the structural memory of the exact point of collapse in the parent universe, the physical impression left behind when an entire cosmos worth of matter was crushed down through an event horizon and forced to erupt into a new spatial dimension. Think of what happens to matter when it falls into a black hole from the perspective of the universe outside. To an external observer, anything crossing the event horizon is frozen in time, its information stretched across the boundary, seemingly lost forever as the black hole eventually evaporates over trillions of years via Hawking radiation. But from the perspective of the matter itself, the journey doesn't stop at the horizon. You continue falling inward, drawn toward the center by an inescapable gravitational current. In Einstein's classical framework, that journey ends in absolute destruction at a mathematical point of infinite density. But infinity is a mathematical ghost. It is the sound of a theory screaming that it doesn't know what happens next. When you introduce the corrections of loop quantum gravity or string theory, space itself cannot be infinitely compressed. It has a fundamental grain size, a minimum limit known as the Planck length. When a collapsing star or an entire galactic center hits that absolute density floor, the fabric of spacetime behaves like a hypercompressed spring. It cannot go any further. The immense gravitational energy doesn't just sit there. It undergoes a radical phase transition, a geometric inversion known as torsion. Instead of continuing to pull inward, the force flips, exploding outward into a completely new set of spatial directions that did not exist before the collapse. This is the cosmic bounce. The matter that fell into the black hole is violently re-accelerated, bursting outward in a spectacular expansion. To anyone sitting inside that newly carved-out space, the expansion looks identical to a Big Bang. The boundaries of the black hole's event horizon become the outer boundary of the new universe's observable horizon. The absolute beginning of our time is nothing more than the final dying echo of a clock that ran out in a world we can never visit. If this description of reality is accurate, it completely redefines what we mean by the word universe. The cosmos is no longer a single, isolated bubble that randomly popped into existence out of a true nothingness. Instead, reality is an interconnected, multi-generational web of worlds, a fractal tree of spacetimes where every black hole formed in our universe is the birthplace of a new child universe expanding into its own private dimensions, entirely hidden from our view. And we, in turn, are living inside the dark, dense heart of a black hole that belongs to a grander, older parent galaxy. This explains the ultimate paradox of the James Webb observations, the conflict between isotropy and asymmetry. For a century, cosmology worked because on the largest scales, everything looked beautifully uniform. The universe seemed to have no center and no edge, expanding evenly in every direction. But James Webb has peeled back the first layer of that uniformity to reveal a subtle, persistent bias in the spin of the oldest structures. This is exactly what you would expect if you were living inside a rotating black hole. On a local level, the space around you feels vast, empty, and uniform. But on the grandest, most ancient scales, the space itself is dragging. It carries the residual angular momentum of the parent star that collapsed to create it. The galaxies forming within our universe are like leaves caught in a vast, slow whirlpool. They spin more frequently in one direction, not because of a local force, but because the very stage they are standing on is rotating. This realization brings a strange, grounding comfort to the scale of the cosmos. When we look out at the cold, silent expanses of deep space, it is easy to feel entirely insignificant, a microscopic flash of biological awareness trapped on a tiny rock, drifting through an indifferent, random void that began by accident and will eventually fade into a cold, dark, maximum entropy death. The Standard Model gives us a universe born in chaos, moving toward chaos, indifferent to structure. But the anomalies found by James Webb suggest a different narrative. They suggest that the universe is not a random accident. It is an organism with a lineage. It has a history that predates its birth, and it carries the physical traits of its ancestors written into the very rotation of its oldest galaxies. Every atom in your body, the iron in your blood, the oxygen you are breathing right now, was forged inside the nuclear furnaces of ancient stars. But if this new paradigm holds true, those stars were only able to form because the fabric of our space-time was shaped, sculpted, and set in motion by a parent universe that came before us. The structure of reality is a continuous line of inheritance, an unbroken chain of cosmic life, giving birth to cosmic life. We are not a lonely anomaly existing in a cold, dead void. We are part of an endless, shifting network of worlds, an infinite sequence of universes nesting inside universes, stretching backward into an unimaginable past and forward into an endless future. Every time a massive star dies in our sky and collapses into a black hole, we aren't just witnessing an end, we are witnessing a beginning. We are watching the birth of an entirely new cosmos, pristine, untouched, and waiting for its own stars to ignite inside the dark. This structural continuity means that the universe we observe is not a closed loop, but an open channel feeding from a reservoir of cosmic history we are only just beginning to decode. When we look at the cosmic timeline through the lens of this new paradigm, the very concept of a primordial era takes on a completely different meaning. In the traditional narrative, the early universe was a place of radical simplicity, a smooth, featureless expanse of cooling plasma where nothing of substance had yet occurred. It was a blank slate. But the data from the James Webb Space Telescope suggests that the early universe was actually a place of intense, concentrated complexity, carrying a high-fidelity imprint of an entire pre-existing reality. The patterns we are discovering in the deep universe are not the first tentative scribbles of a newborn reality. They are the compressed, translated remnants of an entire cosmic epoch that concluded before our own Big Bang even began. To understand how this translation of information occurs across the boundary of an event horizon, we have to look closely at the physics of extreme gravitational environments. When an enormous mass collapses in a parent universe, it doesn't just pull matter toward a central point, it twists the very geometry of space and time into a catastrophic knot. In standard general relativity, This twisting increases without limit until it creates a singularity, a place where the curvature of space-time becomes infinite. But physicists have long suspected that infinity is not a physical reality, but rather a theoretical breakdown. When we look at this collapse through the framework of loop quantum gravity, we find that space-time is not a smooth, infinitely divisible fabric. Instead, it is composed of tiny, discrete, indivisible packets of geometry, fundamental units of space that cannot be compressed beyond a certain point. When the matter falling into a black hole reaches this fundamental quantum density floor, it encounters an immense quantum pressure. The gravity becomes so intense that it actually forces the geometry of space to undergo a topological inversion. The collapse doesn't stop. It turns itself inside out. The space that was contracting under the immense weight of the collapsing star suddenly finds a new direction to expand, opening up an entirely new spatial volume that exists orthogonal to the dimensions of the parent universe. This is the mechanism of the cosmic bounce, a process where the extreme inbound momentum of a dying cosmos is instantaneously converted into the outbound, explosive expansion of a new one. This means that the Big Bang was not an explosion in space, but rather the explosive creation of space, driven by the geometric recoil of a collapsing world. And because this expansion is the direct consequence of a specific physical collapse, the newborn universe cannot start with a clean slate. It is physically bound to inherit the precise structural characteristics of the environment that birthed it. If the parent star or the galactic core that collapsed was rotating, that rotational energy cannot simply vanish into nothingness. The conservation of angular momentum requires that the spin be preserved. As the new space expands inward past the event horizon, the global rotation of the parent system is printed directly into the metric of the new spacetime, creating a subtle, persistent drag that influences everything that forms within it. This is the hidden hand that James Webb has suddenly made visible. When we observe a statistical preference in the spin directions of the earliest spiral galaxies, we are looking at the direct physical manifestation of this inherited angular momentum. The galaxies are not choosing a direction at random, nor are they responding to a local magnetic or gravitational force within our own universe. They are aligning themselves with the primordial rotation of the parent cosmos that collapsed to create our world. It is a cosmic orientation, a global alignment that cuts across billions of light-years of space, revealing that the entire fabric of our universe carries a subtle, permanent handedness. This realization fundamentally challenges the isotropic assumption that has guided cosmology for more than a century. We have always built our models on the belief that if you look at a large enough volume of the universe, any one direction will look identical to any other. This assumption was essential for making the mathematics of Einstein's equations manageable, allowing us to treat the entire cosmos as a uniform, smoothly expanding fluid. But if the universe has a built-in direction, if it carries a global rotational bias, then that uniformity is an illusion born of a limited perspective. The universe isn't perfectly symmetrical. It has a spine, an axis of orientation that connects its deepest history to its current expansion. If this axis of orientation is real, it means that our position in the cosmos is far more specific than we ever imagined. We are not just drifting through a random, featureless expanse of space. We are positioned within a highly structured, directional flow that originates at the very moment of our universe's birth. This directional bias would naturally create subtle variations in the way matter distributed itself during the initial moments of cosmic expansion, explaining why James Webb keeps finding large, highly organized structures in regions of the sky where the standard model predicts only empty gas. The matter didn't have to wander blindly through a featureless void, waiting for random encounters to build the first galaxies. It was guided from the very beginning by the structural channels carved into spacetime by the collapse of the parent universe. This top-down mechanism completely changes the way we interpret the presence of supermassive black holes in the early universe. For decades, astronomers have been locked in a fierce debate over how these monstrous objects could have grown so large so quickly. In the modern universe, a supermassive black hole takes billions of years to accumulate millions or billions of solar masses of material, swallowing gas and stars in a slow, metered diet dictated by the radiation limits of accretion disks. But James Webb has discovered that these monsters were already fully formed and actively feeding just a few 100 million years after the Big Bang, buried inside the dense, crimson cocoons of the little red dots. Under the framework of an inherited universe, these early black holes are no longer a mystery. They didn't grow from small stellar remnants over millions of years. They were never small to begin with. They are primordial seeds, heavy structural fragments that survive the phase transition of the cosmic bounce. When the parent universe collapsed, the densest regions of that world did not completely dissolve into the uniform energy of the Big Bang. Instead, they passed through the geometric inversion as intact, highly concentrated nodes of gravity, instantaneous black holes that found themselves embedded in the rapidly expanding space of the new cosmos. They were present at day one, acting as massive, prefabricated anchors around which the first galaxies could immediately organize themselves. This explains why the early universe appears so shockingly mature, so completely developed, and so rich with heavy elements. The little red dots are the visible signatures of these primordial engines at work, pulling vast reserves of pristine hydrogen into their gravitational wells and igniting intense, hyper-efficient bursts of star formation. These weren't the slow, chaotic star clusters we expected to find. They were dense, high-pressure environments where multiple generations of massive stars could live, fuse heavy elements, and explode in a rapid, generational sequence that compressed billions of years of chemical evolution into a mere fraction of the time. This interconnected vision of reality fundamentally rewrites the final chapter of our own cosmic story. In the standard cosmological model, the future of the universe is a bleak, lonely progression toward a state known as heat death or maximum entropy. As space continues to expand at an accelerating rate, driven by the mysterious pressure of dark energy, galaxies will eventually drift so far apart that their light will no longer be able to reach one another. The stars will burn through their nuclear fuel, grow cold, and fade into darkness. The universe will become a vast, frozen expanse of isolated black holes, which will themselves slowly evaporate over unimaginable eons via Hawking radiation, leaving behind nothing but a thin, cold mist of elementary particles diluting into an infinite, silent void. It is a story of absolute termination, an ending with no echoes and no purpose. But if our universe is part of a grander, nested architecture of black hole cosmology, then the death of a universe is never an absolute end. It is merely the distribution of its material into new generations of space. The accelerating expansion we experience as dark energy might not be an intrinsic property of our own space, but rather the gravitational pull of the parent universe outside our event horizon, or the natural kinetic momentum of the cosmic bounce still carrying us outward. And the black holes that are currently gathering matter at the centers of our galaxies are not cosmic dead ends. They are active incubators, local regions, where the density of spacetime is being compressed toward a new phase transition. Every time a massive star collapses in our night sky, or two supermassive black holes merge in a violent ripple of gravitational waves, the physics of that collapse is preparing the ground for a new creation event. Hidden behind the impenetrable shield of the event horizon, away from our sight and our instruments, the immense pressure is forcing space to turn itself inside out once again. A new Planck density floor is being reached, a new geometric torsion is flipping the gravitational arrow, and a new Big Bang is erupting into an entirely separate set of dimensions. A new child universe is being born, inheriting the mass, the charge, and the rotational momentum of the matter that fell into our black hole. This means that the story of our existence is written into a continuous, infinite lineage of creation. We are the descendants of an ancient cosmos that collapsed to give us birth, and we are currently carrying the seeds of countless future worlds within the dark pockets of our own space. The universe is not a lonely, accidental flash of light in an endless darkness. It is an eternal, self-sustaining tree of realities, constantly branching, constantly evolving, and constantly passing its structural memory down through the fabric of space-time. When we look up at the night sky and see the faint, ancient light of the earliest galaxies captured by James Webb, we are not looking at a dead past. We are looking at our own cosmic heritage, witnessing the moment when the momentum of an older world first woke up and began to shape the stars that made us who we are today. This cosmic lineage transforms the very nature of empty space from a passive void into a dynamic, pressurized medium that remembers where it came from. In our classical understanding, vacuum is defined by its emptiness, a zero-point baseline from which all physical measurements begin. But if our reality is nested inside a parent structure, then the vacuum of our universe is not truly empty. It is a highly tuned relic state. It carries a residual tension, a baseline quantum stress, inherited from the extreme compression of the birth event. This inherited vacuum tension could hold the answer to one of the most embarrassing crises in modern physics, the cosmological constant problem, where our calculated value for the energy of the vacuum misses the observed acceleration of the universe by a staggering factor of 120 orders of magnitude. If the vacuum energy we measure isn't an intrinsic property of an isolated space, but rather the faint, remaining pressure of a parent universe's gravitational collapse leaking through the horizon, the mathematical mismatch ceases to be a paradox. It becomes a localized boundary condition. We are experiencing the dying gasp of a grander compression, scaled down and diluted by the massive spatial dimensions that opened up during our own cosmic bounce. The accelerating expansion we attribute to a mysterious, unexplained dark energy is suddenly revealed to be the natural, long-term kinetic momentum of that initial recoil, a slow unfolding of space that continues to slide down the gravitational gradient established by the ancestral cosmos. This shift from an accidental universe to an inherited universe changes how we analyze the distribution of matter across the cosmic web. When we look at the largest scales of our universe, galaxies aren't scattered haphazardly like spilled ink. They are arranged in an intricate, interconnected network of giant filaments and dense nodes, separated by vast, spherical voids millions of light-years across. Standard cosmology explains this web as the result of tiny dark matter fluctuations that grew over billions of years, slowly pulling gas into the highest density regions. It is a compelling story, but it struggles to explain the sheer scale and rapid crystallization of these cosmic walls in the early epochs caught by James Webb. In an inherited model, the cosmic web isn't an original structure built from scratch. It is a ghost print. When the parent star or galactic core collapsed in the previous universe, it didn't collapse symmetrically. The matter fell inward along preferential planes of structural failure, driven by the internal rotation, magnetic fields, and density variations of the parent system. When that collapsing mass hit the Planck density floor and bounced, the shock waves traveled along those exact pre-existing lines of geometric stress. The expanding universe didn't create a new web. It simply inflated the fracture lines of the old one. The filaments where galaxies cluster today are the structural seams left behind by the collapse of our cosmic parent, acting as pre-carved superhighways that guided the primal gas into massive, organized cities while the clock of our universe was barely ticking. This mechanism changes our perspective on the nature of dark matter itself. For generations, dark matter has been treated as an undiscovered, invisible particle that dominates the gravitational budget of the universe, hiding from our particle accelerators while holding galaxies together. But despite decades of searching, these phantom particles remain entirely undetected. Black hole cosmology offers a radical alternative. What if the missing gravity we attribute to dark matter isn't caused by clouds of undiscovered particles at all? but is instead the gravitational shadow of the parent universe pressing against our horizon. If our spacetime is bound within the interior of an event horizon, the massive distribution of matter in the universe outside our bubble would still exert a profound tidal influence on the geometry of our space. This external gravitational pull would distort our local spacetime metric, creating localized regions of increased gravitational curvature that do not correspond to any visible matter within our universe. To an astronomer sitting inside the bubble, this unexpected bending of light and rapid rotation of galaxies would look exactly like the gravitational pull of an invisible, non-interactive form of matter. We wouldn't be able to find a dark matter particle in a laboratory because dark matter isn't a particle. It is a macro-structural reflection of the grander universe nesting around us, a constant reminder that our reality is being cradled by a larger architecture. This realization brings a staggering weight to the little red dots that James Webb continues to unearth across the early universe. These hypercompact crimson engines are no longer just an anomalous phase of early galactic evolution. They are the physical junction points, where the transition between the old universe and the new universe occurred. They are the cosmic conduits through which the matter and energy of a dying world were funneled, compressed, and re-radiated into our expanding space. When we observe these dots glowing intensely in the infrared while remaining completely dark in the X-ray spectrum, we are looking at the literal smoke from the cosmic furnace, the dense cocoons of primordial gas being violently reorganized by gravity that existed before the concept of time was even defined in our world. These primordial engines didn't just accelerate the formation of stars, they fundamentally altered the rules of stellar chemistry. In the standard model of cosmology, the first stars, population 3 stars, were supposed to be pure, untouched giants made entirely of hydrogen and helium. Because they lacked heavy elements to help cool the gas clouds during collapse, they had to grow into unstable monsters hundreds of times more massive than our Sun, burning through their fuel in a few million years before exploding and scattering the very first traces of carbon, oxygen, and iron into the void. It was supposed to take multiple rounds of this stellar birth and death before a galaxy could achieve the chemical richness required to build stable disks, rocky planets, and life. But James Webb's spectroscopic instruments are finding complex chemical enrichment in galaxies that existed when the universe was less than 5% of its current age. The heavy elements are already there, deeply woven into the oldest stellar populations. In an inherited universe, this chemical maturity is precisely what you would expect. The cosmic bounce didn't completely disintegrate the matter of the parent universe into fundamental particles. It was a phase transition, an intense nuclear restructuring. The extreme temperatures and pressures of the bounce would act as a universal nucleosynthesis event, a hyperfurnace that forged heavy elements directly out of the collapsing material before the expansion even began. The first stars in our universe didn't have to start with pure primitive hydrogen. They were born from a chemically rich inherited soil, allowing complex stellar systems and planetary building blocks to exist almost immediately. This fundamentally shifts the timeline for the emergence of complexity and life across the cosmos. In the traditional narrative, life is a late-stage addition to the universe, a rare cosmic accident that had to wait billions of years for the harsh, violent conditions of the early cosmos to settle down, and for enough stellar generations to die and enrich the interstellar medium. We were taught that we live in a young, immature universe that is only just beginning to develop the capacity for intelligence and self-awareness. But if the universe carries an inherited blueprint, then the capacity for complexity is built into the very fabric of space-time from day one. The universe didn't have to learn how to build structure through billions of years of random trials. It remembered how to do it. The conditions necessary for the formation of stable stars, rocky worlds, and complex chemical networks were present from the very opening acts of the cosmic expansion. We are not living in a fragile, early experiment at the beginning of time. We are living in a mature, deeply refined iteration of an eternal, self-sustaining system that has been processing information, structure, and complexity across countless generations of universes. This continuity completely changes our relationship with the black holes that inhabit our own modern universe. When we map the supermassive black hole at the center of the Milky Way, or watch distant telescopes capture the shadow of the event horizon in the heart of M87, we are no longer looking at destructive, apocalyptic voids where reality goes to die. We are looking at the back doors of our universe, the birth canals of tomorrow. The matter that falls into those black holes today, the dust, the gas, the light of dying stars, is not being erased from existence. It is being collected, compressed, and prepared for the next great phase transition. Hidden behind those dark horizons, away from our sight, the exact same physics that built our world is repeating itself. The inbound matter is hurtling toward a new Planck limit, the geometric spring is compressing, and the arrow of gravity is preparing to flip. A new set of dimensions is opening up, completely isolated from our own space, and a new Big Bang is erupting into the dark. Those child universes will inherit the mass of the stars our black holes swallow. They will inherit the electric charge of our interstellar gas. And if our galaxies are spinning, those newborn worlds will inherit our angular momentum, printing the rotation of the Milky Way. What intrigues astronomers is the implication. If little red dots represent the primary black hole growth phase, and if that phase is most vigorous in the early universe, then black holes assembled their mass quickly, not gradually, not carefully, rapidly, violently, almost as if the early universe was optimized for black hole production, as if the physical conditions favored feeding and growth above all else. That fits naturally with black hole cosmology. If universes reproduce through black holes, then universes that grow black holes fastest leave most descendants. Selection would favor conditions enabling rapid black hole assembly. Webb's little red dots may be evidence of that selection operating in real time. The universe building the very structures that will birth its successors almost before structure itself has fully formed. The impossible age. But beneath all these mysteries lies a simpler, more fundamental problem. The universe may be too young. Not literally. The universe is genuinely 8 billion years old, according to standard measurements. But that age is calculated based on assumptions about how space expands. And if the expansion history is more complicated than we understood, the true age might differ significantly. This connects to the Hubble tension. The expansion rate of the universe can be measured two different ways. The first method looks at the early universe. Specifically, the cosmic microwave background, the ancient thermal radiation, released about 380,000 years after the Big Bang. By analyzing fluctuations in that radiation and applying the standard cosmological model, scientists can calculate what the current expansion rate should be. That calculation gives approximately 67 kilometers per second per megaparsec of distance. The second method looks at the nearby universe. It measures distances to galaxies using variable stars and supernova explosions, then compares those distances to recession velocities. That measurement gives approximately 73 kilometers per second per megaparsec. The difference is about 9%. In everyday terms, 9% is negligible. In cosmology, 9% breaks the model. Expansion rate determines the age of the universe. A faster expansion rate means the universe reached its current size more quickly. Slower expansion means it took longer. If the expansion rate is uncertain, then age becomes uncertain. And if age is uncertain, then the entire cosmic timeline becomes uncertain. Some physicists now propose that the universe may be significantly older than 8 billion years. Not by a little, by a lot. Some models suggest 20 or 26 billion years, nearly double the standard estimate. That would be radical. It would change everything. The age scale is woven into every cosmic calculation. Change the age, and everything else shifts. But an older universe explains many of Webb's anomalies beautifully. Mature galaxies stop being impossible. Chemical enrichment becomes less problematic. Black hole growth becomes easier. The little red dots fit more naturally. Heavy elements have more time to accumulate. Structure has more time to organize. The impossible begins looking merely improbable. Yet mainstream cosmology resists age extension because the cost of being wrong is enormous. Every major cosmological model depends on the age scale. The cosmic microwave background, nucleosynthesis calculations, galaxy clustering, dark matter distribution, all of these rest on precise age measurements. Pull that thread, and the entire framework shifts. Some pieces will need reworking. Some may need replacement. Still, the pressure from Webb is real, and under that pressure, ideas that were once fringe are moving toward the center of serious discussion. Because when observations refuse to fit the model, scientists must ask the difficult questions. Not small questions, big ones. Is the age really 13? 8 billion years? Or have we been reading the cosmic clock incorrectly all along? The reluctant heresy. That question leads to another. What if some portion of redshift comes from something other than expansion? Decades ago, some physicists proposed that photons might lose tiny amounts of energy as they travel vast distances, not because of expansion, but through subtle interactions with space-time. This became known as tired light. For decades, mainstream science rejected it because it failed multiple observational tests. But Webb's anomalies have revived interest in modern versions. The idea is not that expansion does not happen. Expansion clearly occurs. Rather, the idea is that expansion may be only part of the story. Some redshift may come from photons losing energy over billions of years of travel. If even a small fraction comes from such energy loss, rather than pure expansion, then distant galaxies may be closer in time than they appear. The cosmic clock would need adjustment. That adjustment would be radical. It would affect distance calculations. It would alter the interpretation of how fast the universe expands. It would change how we measure the ages of the oldest galaxies. Yet it would elegantly solve several of Webb's problems simultaneously. Galaxies that appear too mature would have had more time to mature. Black holes that appear too massive would have had more time to grow. Chemical enrichment that appears too complete would have had more time to accumulate. The cost of adopting tired light would also be enormous. Multiple cosmological pillars rest on standard expansion interpretation. The cosmic microwave background fits expansion theory beautifully. The light curves of distant supernovae show time dilation exactly as expansion predicts. Any alternative mechanism must account for these observations too. That is a heavy burden. Yet the fact that Webb has made serious scientists revisit tired light at all speaks volumes. The discomfort with the standard model is genuine. The anomalies are real. The pressure to explain them is mounting. And that pressure is forcing cosmology to confront its assumptions. The dark matter question. But the most unsettling possibility involves dark matter itself. For nearly a century, dark matter has been cosmology's invisible engineer. It does not shine. It does not absorb light. It interacts only through gravity. Yet without it, galaxies should not exist. Stars should orbit too slowly. The universe should look fundamentally different. The standard model assumes dark matter is cold, meaning slow-moving, meaning it clumps readily into dense knots. Those knots become the gravitational seeds around which galaxies form. The standard picture envisions small clumps coalescing into larger structures over billions of years, hierarchical structure formation, from the bottom up. Yet Webb's earliest galaxies are not small and clumpy. Some appear elongated, some appear filamentary. Some stretch across space in ways that suggest they formed along smooth channels rather than within dense clumps. That pattern matches predictions from alternative dark matter models far better than cold dark matter can explain. Wave dark matter offers one alternative. In this model, dark matter particles are so light that their quantum wavelengths stretch across entire galaxies. Instead of behaving like individual particles, dark matter behaves like a wave, a smooth oscillating field, a quantum ocean. Wave-like dark matter forms smooth filaments rather than tight clumps. Gas flows along those filaments naturally. Galaxies form as elongated structures along the filaments, exactly the shapes Webb observes. If dark matter is wave-like, then decades of particle detection experiments have been looking for the wrong thing. Most searches focus on heavy particles. Underground detectors search for rare collisions with normal matter. Nothing has been found. Wave dark matter would explain that failure. Ultralight particles barely interact at all. Their presence reveals itself only through structure, through gravity, through the shapes of galaxies. Webb may be providing that evidence, not through detection, but through observation of structural consequences. The elongated galaxies Webb finds in the early universe may be telling us that dark matter is not cold particles, but quantum waves. That revelation would reshape dark matter theory entirely, the missing ingredient. But there is another possibility, even stranger than wave dark matter. What if some portion of dark matter is made of primordial black holes? Ancient black holes formed in the first seconds after the Big Bang, before stars, before galaxies, before light moved freely. These objects would be completely invisible unless actively feeding. They would interact purely gravitationally. They could act as seeds for galaxy formation. They could contribute to the invisible matter holding galaxies together. That possibility would connect multiple mysteries. Early black holes would have their seeds explained. Galaxy formation would have its accelerant provided. Dark matter would have an additional component identified, and the little red dots would be more understandable as active feeding phases around primordial seeds. Suddenly, separate anomalies begin linking into a coherent picture. Not one that is certainly true, but one that hangs together. One that explains multiple observations without requiring numerous independent adjustments. That is the moment when speculative ideas become worth serious consideration, the structure of memory. But beneath all these physical mysteries lies something even more profound: the question of memory itself. In physics, motion carries history. Rotation preserves information. A spinning object contains encoded information about the forces that set it spinning. If the universe is born rotating, that rotation is inherited information. A memory of the parent universe is motion. The cosmic microwave background is memory too. Ancient photons preserving the temperature fluctuations of the infant universe. Light itself carrying pattern across billions of years. Every galaxy is memory, every stellar population, every chemical abundance. The universe is built from memory made visible. Webb's rotational asymmetry may be the deepest memory of all, a signature written into space-time itself at the moment of cosmic transition, a fingerprint from before what we call the beginning. Not conscious memory, not intentional preservation, structural memory. The kind that persists because of conservation laws that cannot be broken. Angular momentum cannot vanish. It cannot be created from nothing. If it is present, it has ancestry. If the galaxy rotation preference is real, then memory from before our Big Bang is present in our cosmos. That is not merely an astronomical observation. That is evidence of continuity, of inheritance, of something larger than the universe itself containing our universe, of a chain that extends beyond visibility, beyond our theoretical horizon. The recursive infinite, the deepest implication of black hole cosmology, is almost impossible to contemplate. If every black hole contains a universe, and if every universe contains black holes, then reality is recursive. It branches infinitely inward, universes within universes, within universes. A structure so deep that absolute origin becomes meaningless. There may have never been a first universe. Reality may be eternally recursive. Each universe born from a black hole in a parent universe. Each black hole creating child universes. Forward and backward, simultaneously, infinite levels of nesting, causality woven in impossible loops. That idea removes the need for creation from nothing. It removes the singularity problem. It eliminates the infinities that plague current theory. But it replaces them with something equally unsettling. An infinite chain of causality with no beginning point. A reality that is self-creating. That exists not because something created it, but because its own structure demands its existence. Webb does not prove this. But by showing early universes optimized for black hole production, by revealing rapid structure formation, by exposing rotational memory, by displaying little red dots that may be black hole nurseries, Webb points toward this possibility. Each observation, alone, could be explained away. Together they whisper of something deeper, the temporal question. The final mystery is time itself. We experience time as flowing forward. Memories point backward. We cannot change the past. The future remains open. That asymmetry feels fundamental. But in physics, time is strange. At the quantum level, equations work equally well forward and backward. Time reversal symmetry. Only when we aggregate billions of atoms does time develop direction. If the universe is born from a black hole in another universe, time inherits its direction from the parent. Matter falling through an event horizon can only move one way, in toward the center. That one-way motion gives the interior universe temporal direction. Time becomes a consequence of geometry, not fundamental, not ultimate, derived. The arrow of time becomes inheritance, something passed down like genetics, from parent universe to child. Forward direction woven into the structure of space itself. And if time is inherited, then it can vary between universes. Child universes may have different time rates, different temporal structure, different relationship to causality. That means our experience of time flowing forward is not universal truth, it is local property, specific to our cosmos, inherited from the geometry we were born into. Webb cannot measure time itself, but by suggesting we may live in a universe born from collapse, it implies time itself is not what we thought. The computation question. If all of this is true, then reality becomes something we are only beginning to understand, not a container of matter moving through fixed space, not a stage where physics plays out, but a process, a calculation, information transforming according to rules. Some physicists now propose that the universe is fundamentally computational, not simulation, not designed, but operation of laws as they process initial conditions into outcomes, rules transforming states, mathematics becoming physical reality. If that is true, then black holes are not monsters, they are data compression engines, places where the universe densifies information. Places where quantum information becomes concentrated to impossible degrees. And when they are so concentrated that collapse approaches singularity, the compression triggers a bounce. Information redistributes. A new universe expands. The computation continues at a new scale. Webb's impossible galaxies would be evidence of efficient computation. Structure organized rapidly, because the information processing was optimized. The little red dots would be evidence of the computational process running at high intensity. Black holes concentrating and redistributing information at maximum speed. And minds like ours would be part of that computation. Self-aware information processing systems, universe studying itself. the computation reaching a stage where it observes its own operation. That is not accident. That is outcome of selection. Universes that develop observers are universes that know themselves. And self-aware universes may function differently than unconscious ones. The inheritance we carry, the atoms of your body, were forged in stars. Those stars were born in galaxies. Those galaxies were seeded by gravitational collapse. That collapse may have come from primordial black holes. Those black holes were born in the first second after the Big Bang. That Big Bang may have been the bounce from a prior contracting universe. That prior universe existed inside a black hole in yet another cosmos. You are made of inherited matter shaped by inherited structure operating under inherited physical laws. Your consciousness is an outcome of inherited physics. Your capacity to think is downstream of inherited capacity for complexity. Your ability to build Webb is a result of inherited tendency toward tool-making intelligence. The entire chain of your existence is inheritance. Not conscious design, not random chance, but systematic selection favoring complexity, favoring structure, favoring the conditions that lead to minds. You exist because your universe is the kind of universe that creates observers. And your universe is that kind of universe because it is the offspring of countless parent universes selected for their capacity to generate such offspring. That is not destiny. That is statistics. Evolution applied to the multiverse, the cosmos breeding itself more efficiently each generation, becoming better at creating structure, better at building observers, better at generating conditions for thought. And you are the current expression of that evolutionary process, not the culmination, not the goal, just the latest stage. The universe is not finished yet. Selection is ongoing. Future generations of universes will be even more optimized for structure. Future observers will be even more capable of understanding their cosmos. The question Webb left unanswered. James Webb did not solve the cosmic mystery. It deepened it. It revealed cracks in theories we thought complete. It exposed blind spots in assumptions we thought certain. It made the invisible universe slightly more visible while simultaneously making it seem stranger. The immediate future will bring more telescopes. The Roman Space Telescope will map vast regions of sky with high precision. The extremely large telescope will dissect distant galaxies in unprecedented detail. The Vera Rubin Observatory will chart structure on scales never before achieved. Each instrument will attack different aspects of the puzzle. Some of today's ideas may survive. Black hole cosmology may become central. Primordial black holes may be confirmed. Wave dark matter may replace cold dark matter. An older universe may necessitate cosmological revision, or all of these may fall away as better data arrives. That is the way science works. Ideas are provisional, hypotheses are temporary, only data is real. But Webb has already changed something fundamental. It has made the unknown feel larger again. For decades, cosmology had achieved a kind of closure. The standard model explained most things. Dark matter solved the missing mass problem. Dark energy explained acceleration. Inflation explained uniformity. There were gaps, but they seemed manageable, solvable within the existing framework. Webb has opened those gaps wider, made them seem less solvable by incremental improvement, made them seem like evidence of something more fundamentally incomplete. The cracks are no longer small, they are becoming structural. What comes next? The greatest revolution in science often does not happen when a theory is proven wrong. It happens when a theory is proven incomplete. When a framework that worked beautifully in its domain is revealed to be a special case of something larger. That is what happened when Einstein extended Newton. Not that Newton was wrong, but that Newton was incomplete. That deeper structure existed beneath the gravitational equations. Something similar may be happening now. The Big Bang model is not wrong. It explains enormous amounts of data. But it may be incomplete. black holes, bouncing universes, recursive reality, inherited laws. These are not replacements for the Big Bang. These are possible deeper layers beneath it. Webb is forcing cosmology toward that realization, not through proof, but through accumulated pressure, through anomalies that do not fit cleanly, through questions that cannot be dismissed, through data that refuses to match prediction. The next decade will determine what happens next. Will the standard model adjust gracefully around the anomalies? Will dark matter transform into wave form? Will the age expand? Will primordial black holes be confirmed? Will multiple revisions come simultaneously? No one knows. But the question has moved from, how do we fine-tune our existing model, to, is our existing model even approximately correct at deep levels? That is the shift that precedes revolution. That is how paradigm change begins. The personal universe. You are living in the era when the cosmos stopped hiding. When light that began traveling billions of years ago finally reached instruments capable of revealing its secrets. When human curiosity built machines powerful enough to see into cosmic history and ask questions that threaten to rewrite our understanding of existence. The magnitude of that moment is easy to miss in daily life. You wake up, you work, you sleep. The universe seems unchanged. The sun rises where it always did. The stars twinkle as they always have. The ground beneath your feet feels solid and permanent. But in the deep sky, gravity is reshaping reality. Galaxies are colliding and merging. Black holes are feeding and growing. Stars are exploding and creating heavy elements. The entire cosmos is in motion, transformation, evolution. And through Webb, that cosmic drama has become visible. Ancient light arriving with messages, structures revealed, mysteries exposed. You are made of that cosmos. The carbon in your cells was forged in stellar cores. The oxygen in your blood came from supernovae. The iron in your proteins formed in dying stars. Every atom of your body has been recycled through cosmic processes into the spin of galaxies that won't form for trillions of years in a reality we will never touch. This endless, branching cascade of worlds transforms the concept of eternity from a cold, flat infinity into a living, evolving ecosystem. The cosmos is not moving toward a silent, frozen death of maximum entropy, because entropy is bounded by the horizon of each individual universe. Every time a new bounce occurs, the local clock is reset, the energy is reconcentrated, and a pristine, high-energy dawn is initiated inside a new event horizon. The tree of realities remains eternally green, constantly shedding its old, cold, expanded branches while budding new, vibrant universes in the deep centers of its gravitational wells. We are part of this grand, breathing structure, a single generation, in an infinite line of cosmic inheritance. Every atom in our bodies, the calcium in our bones, the carbon in our DNA, carries the physical memory of this eternal cycle. They were forged in stars that were guided by a primordial rotation, seeded by black holes that survived a cosmic bounce, and set in motion by a parent universe that came before the dawn of our time. When we look out into the deep night sky through the eyes of the James Webb Space Telescope and find structures that shatter our oldest assumptions, we do not need to feel alarmed by the impossible questions they raise. We are simply recognizing our own origins, looking past the horizon of our local beginning and catching the very first glimpses of our true, ancient home. This structural inheritance means that the fundamental constants of nature, the speed of light, the strength of gravity, the mass of an electron, might not be arbitrary numbers chosen by a cosmic dice roll at the moment of the Big Bang. In standard physics, these values are treated as brute facts, fine-tuned parameters that just happen to fall within the narrow window necessary for the existence of chemistry, stars, and life. If you alter them even slightly, atoms fly apart, stars burn out instantly, or the universe collapses back into a crunch before anything can form. This fine-tuning problem has forced many cosmologists to adopt the multiverse hypothesis, a theory suggesting that an infinite number of parallel universes exist, each with entirely random laws of physics, and we simply happen to occupy one of the few stable bubbles capable of supporting observers. But black hole cosmology replaces the random lottery of the multiverse with a mechanism of cosmic evolution and natural selection. If a child universe is born from the core collapse of a parent system, the structural inversion of the cosmic bounce cannot completely rewrite the underlying physics. The quantum geometry of the Planck density floor acts as a filter, allowing certain structural traits to pass through while suppressing others. The physical parameters of the child universe are directly determined by the quantum state of the collapsing matter. A universe with physical laws that favor the creation of massive stars and dense galactic cores will naturally produce a vast number of black holes, with each black hole acting as a seed for a new child universe. Through this process, the laws of physics themselves undergo a form of generational refinement. Universes that possess parameters capable of generating rich, complex structure and dense gravitational nodes reproduce at an exponential rate, populating the wider tree of reality with worlds optimized for complexity. Universes with sterile parameters, those that expand too quickly for gravity to work or collapse back into a singularity before stars can ignite, fail to create black holes and become evolutionary dead ends. We live in a universe perfectly tuned for stars, heavy chemistry, and life, not because of a lucky accident in an infinite sea of random bubbles, but because our universe inherited its structural operating system from an incredibly long line of highly successful ancestors that mastered the art of cosmic reproduction. This framework sheds light on another deep mystery of the early universe: the distribution and nature of primordial magnetic fields. For decades, when mapping the vast spaces between galaxies, astronomers have detected weak but widespread magnetic fields stretching across millions of light-years of empty space. These fields are distinct from the localized, intense magnetism generated by modern stars and active galactic nuclei. They are a permanent feature of the deep cosmic background, present even in the most remote intergalactic voids where no galaxy has ever traveled. Standard cosmological models have a notoriously difficult time explaining the origin of these seed fields, as a perfectly smooth, uniform Big Bang provides no mechanism for generating large-scale magnetic alignment across billions of light-years of space. In an inherited universe, these cosmic magnetic fields are the preserved fossil currents of the parent universe. When the ancestral core collapsed, the immense electrical currents and plasma flows of that dying system were crushed down into the Planck density interior of the event horizon. As the geometry inverted and the cosmic bounce initiated the expansion of our space, those magnetic field lines were caught in the fabric of the expanding spacetime. They didn't form after the Big Bang. They were stretched, diluted, and distributed across our newborn cosmos during the initial fraction of a second of inflation. They provided a global magnetic grid that existed before the first star ever ignited, acting as an invisible template that helped guide the primal gas into the dense, structured filaments observed by the James Webb Space Telescope. This continuous transmission of fields and forces across the horizon of creation forces a profound reassessment of the boundary conditions of our universe. We have spent more than a century treating the observable horizon of our cosmos as an absolute, impenetrable wall. We assumed that because light cannot travel faster than the expansion of space, we were fundamentally cut off from any reality existing outside our 46 billion light-year bubble. But if we are living inside a black hole, the boundary of our universe isn't a random edge defined by the speed of light. It is a physical event horizon that is actively experiencing the dynamics of the grander universe nesting around us. This means that our universe is not an isolated system. It is an open, thermodynamic environment that can experience subtle, large-scale, long-term influences from the parent cosmos. If the parent universe experiences a massive gravitational shift, such as the merger of the parent black hole with an even larger supermassive black hole in the ancestral galaxy, the shock waves of that external event would ripple across the event horizon of our world. These external disturbances would manifest in our universe as subtle, large-scale anomalies in the cosmic microwave background, or unexpected, coordinated movements of galaxy clusters over billions of light-years, an effect astronomers sometimes refer to as cosmic flow. We aren't looking at random fluctuations within our system. We are witnessing the distant, muffled thuds of an ongoing cosmic environment playing out in the grander reality that wraps around our world. This brings us back to The Little Red Dots and the Impossible Galaxies Unmasked by James Webb. These objects are telling us that the story of our universe cannot be understood if we keep reading it from page 1. They are forcing us to look at the cover to recognize that our beginning was a consequence of an entirely separate prior chapter. The rapid organization of matter, the hyper-efficient star formation, the early emergence of heavy chemical elements, and the subtle, persistent spin preference across the deepest night are all pointing toward the exact same conclusion. Our universe carries a physical memory. It has a lineage, a heritage, a specific set of inherited traits that allowed it to skip the trial and error phase of a newborn creation and step onto the stage of existence fully prepared to build a complex reality. This realization fundamentally shifts the emotional weight of cosmology. When we look out at the deep universe through the standard model, we are looking at an accidental spark in a cold, indifferent machine that is running down toward an eternity of absolute nothingness. It is a paradigm that alienates human consciousness, framing our existence as a microscopic, temporary fluke on a speck of dust that has no connection to the wider mechanics of the cosmos. But under the paradigm of an inherited, evolving multiverse, the universe ceases to be an indifferent machine. It becomes an ongoing, living tradition. The iron in your blood, the carbon in your cells, and the spark of awareness that allows you to contemplate the stars are all direct continuations of an unbroken chain of cosmic life that has been passed down across generations of universes. The structure of reality didn't just happen by accident. It was built, refined, and set in motion by an infinite lineage of worlds that came before us. We are not outsiders looking in on a cold, mechanical void. We are a part of the inheritance, a local expression of a grander, nested reality that has been finding ways to organize itself, to express complexity, and to look back at its own beginnings since before time even had a name. Every discovery that shatters our oldest assumptions is not a crisis for physics. It is an invitation to look deeper, to follow the trail of impossible questions, and to realize that our connection to the structure of reality is older, stranger, and far more profound than we ever dared to believe. This generational transmission of physical laws means that the universe we inhabit is essentially an optimization engine for complexity. When we look at the cosmic background, we are not looking at a sterile ledger of equations, but at the living canvas of a reality that has survived multiple iterations of cosmic birth. The implications of this framework ripple out into the very way we study quantum mechanics and the macroscopic scale of space, suggesting that the strange, counterintuitive laws of the very small are deeply connected to the macrostructural survival of the very large. The quantum entanglement that links two particles across vast distances might not be an accidental quirk of subatomic physics. It could be the fundamental stitching that holds the fabric of a child universe together during the violent transition of the cosmic bounce. If the quantum state of matter is preserved through the inversion of a black hole collapse, then every particle in our universe carries a subtle, non-local connection to the parent cosmos. This inherited entanglement would manifest as a background quantum noise, a faint, universal baseline that dictates how wave functions collapse and how probabilities manifest in our laboratories. We are swimming in a sea of quantum memory, where the behavior of an electron in a modern experiment is subtly guided by the structural history of a star that died in a world that existed before our own space was born. This gives a profound new meaning to the idea of physical determinism. The universe is not a chaotic clockwork winding down randomly from an accidental beginning. It is a highly coordinated, self-correcting system where the past is never truly lost, but is instead compressed, refined, and woven into the laws of the present. This deep integration of past and present helps explain one of the most stubborn anomalies detected in our own cosmic neighborhood, the axis of evil. When cosmologists mapped the cosmic microwave background with ultra-precise satellites, they noticed a strange, large-scale alignment in the temperature fluctuations of the early universe. Instead of being perfectly random and evenly distributed across the sky, as the standard isotropic model requires, the hot and cold spots seemed to align themselves along a specific cosmic axis. For years, this alignment was dismissed as a statistical fluke, a localized artifact, or a systematic error in our instruments. It was given a dark, cautionary name because it threatened to undermine the very foundation of the Copernican principle, which states that humans do not occupy a special or privileged place in the cosmos. But in the architecture of an inherited universe, this axis is not an evil anomaly. It is the physical spine of our world. It is the geometric line along which the ancestral black hole collapsed, the axis of rotation that guided the inbound matter before it hit the Planck density floor and bounced outward. The alignment in the cosmic microwave background is the literal shadow of that ancestral rotation, a permanent macroscopic marker showing us the direction of the flow that gave birth to our spacetime. When we map this axis, we are not finding a localized violation of physics. We are looking at the orientation of the cosmic birth canal. The universe appears anisotropic because it is anisotropic on the grandest scales, carrying a global orientation that connects our local space to the vast, nesting environment of the parent galaxy outside. This structural orientation provides a radical new framework for understanding the nature of time itself. In classical physics, time is treated as a smooth, continuous line stretching from an absolute past into an absolute future, governed by the law of entropy, which dictates that systems must always move from order to chaos. This creates the famous arrow of time, a one-way street that leads inevitably to the dissolution of all structure. But if our universe is a nested bubble within a larger family tree, then time is not a straight line, but a branching fractal sequence. Local time begins anew, inside every event horizon, initiated by the cosmic bounce that resets the local thermodynamic clock, while the grander parent universe continues its slow, long-term progression toward expansion and decay. The interior of its black holes are constantly sparking fresh, high-energy, low-entropy beginnings. This creates a cosmic ecosystem that is structurally immune to the ultimate death of heat death. The total system never runs out of energy, because energy is constantly being localized, compressed, and recycled through the mechanism of gravitational collapse. A black hole is not a grave where matter is permanently erased. It is a thermodynamic crucible that purifies matter, stripping away the maximum entropy of a dying stellar system and compressing it back into a pristine, high-density, low-entropy state ready to launch a new cosmic dawn. The arrow of time inside our universe is a localized inheritance, a specific generational clock that started ticking when the geometric spring of the cosmic bounce recoiled, allowing us to experience a world of order, growth, and complexity, while surrounded by the ancient momentum of a grander, nesting reality. This structural continuity fundamentally redefines the nature of cosmic isolation. For centuries, our philosophy and our science have been haunted by the silence of the deep universe. We looked out at the billions of light-years of empty space and saw a cold, indifferent void that had no knowledge of our existence, a mechanical stage where we were nothing more than accidental spectators. But James Webb has pulled back the curtain on that loneliness by showing us that the earliest galaxies were already mature, organized, and structurally aligned with a global directional bias. The telescope has revealed that space is not an empty, silent stage. It is an active, breathing medium that is densely packed with the genetic material of an older world. The matter that makes up our modern world, the carbon in our forests, the iron in our architecture, the water in our oceans, is not a random collection of dust that happened to clump together by luck. It is the refined product of an eternal cosmic tradition, shaped by forces that have been perfecting the art of structure across multiple generations of universes. We are structurally connected to the grander cosmos through an unbroken line of physical inheritance, a continuous chain of cosmic life that passes its traits down through the dark, dense hearts of collapsing stars. When we look into the deep universe and find patterns that defy our traditional equations, we are not looking at a broken reality. We are looking at our own history, catching the distant, fading signals of the ancestral home that collapsed so that our world could begin. When we say that James Webb has shattered every model built since Einstein, it is not an indictment of Einstein's genius. Albert Einstein handed us the keys to the cosmos. He showed us that space and time are not a static, unyielding stage, but a flexible, dynamic fabric that bends, warps, and ripples in the presence of mass and energy. His equations of general relativity predicted the expansion of the universe, the existence of black holes, and the delicate warping of time itself. For more than a century, his framework stood as an unassailable fortress.